In the next few lectures, we're going to focus on heat, that transfer of heat between system and surroundings that is a component of what makes up the total change in internal energy. After that, we'll talk about work. So, heat, again, remember, is different than temperature. However, the change in temperature helps us track how heat moves. So, heat is a transfer of energy between system and surroundings. And we notice that transfer of heat when we see the temperature of our system and surroundings change. So, we could say that heat's proportional to a change in temperature. And we can actually create an equality here if we take into account how much energy is required to change the temperature of an object that's the system or something that is the surroundings. And we call that heat capacity. So then heat can be equal to the heat capacity times the change in temperature that occurs for an object or for chemicals in a reaction, something like that. So we're going to define heat capacity, and we're going to give it C as its unit. And it's going to be the quantity of heat that will change the temperature of a system by 1 degree Celsius. Can also think of that as a degree Kelvin, right? Because it's the same scale of temperature, just with a different zero definition. So the larger the heat capacity an object has, then the smaller the temperature rise will be if you put in some energy. So it's like saying that you have to put more energy into something with a high heat capacity to be able to increase its temperature a little bit. And if something has a really low heat capacity, then if you put a little bit of energy in, the temperature changes a lot. And so let's say you were going to pick up an object that had been in the fire. Would you rather pick up an object that had a really high heat capacity or a really low heat capacity, right? If I don't want to get burned, I want the object in the fire to not have actually increased in temperature when it's absorbed a certain amount of heat as much as the other object. And so I'll always pick up something that has a higher heat capacity to protect my hands. So that's heat capacity. There's a few variants on this that we'll use. We'll use specific heat the most. There's also molar heat capacity. And these are heat capacity per gram of a substance if it's specific heat, or per mole of a substance if it's molar heat capacity. So that way we can say this object will increase by this amount in terms of temperature for every gram or for every mole that we have of it. So the larger the object is, the more energy it can absorb before the whole object changes temperature. Let's look at an equation that defines specific heat. So specific heat's that heat capacity per gram of a substance. And so I could actually rewrite that instead of in a sentence as saying it's the specific heat is equal to the heat capacity divided by the grams per, the heat, let's call it that. So specific heat is the heat per gram of a substance. That's the amount of energy that flows, right? And so we can actually arrange this. So looking at heat capacity, we can define it as, or specific heat, we can define it as the heat capacity per gram of a substance. So that means that the amount of heat that flows into a system, so that energy that transfers either into or out of a system, is going to be dependent on the mass of that object or the system, the specific heat capacity of it, so the amount of energy it takes to change the temperature of that object, and times that temperature change. So, and we can rearrange this in a number of ways. You'll sometimes see it written instead as defined by defining heat capacity or specific heat capacity as equal to the heat that transfers into or out of the system divided by the mass of the system and the temperature change for the system as this process takes place. And so we can plug into this equation pretty easily to figure out the amount of energy that would be absorbed by a chemical reaction or that would be released by a chemical reaction. If we know some of our parameters, like how much of it we have, mass, uh, how much the temperature changes over the course of that energy being absorbed or released, and then also that kind of defining feature of the system, the specific heat. And so I've got some examples here on the right-hand side of specific heat capacity for different elements and substances like compounds. You can also measure experimentally the specific heat capacity for a system itself, which you would do experimentally and wouldn't be something you would look up in a table. But you can see things like lead, gold, and silver all have about a 0.1 to 0.2 joules of energy per gram of the substance to increase it 1 degree. And our compounds like ethanol and water, and remember these have bonds actually now, right? And are multiple atoms for each component. And looking at these compounds like ethanol and water, we see a higher heat capacity or specific heat capacity of something on the order of like 2 joules per gram degree Celsius or 4. And so these are things that you'll either be calculating or you'll be given to calculate something else. And we'll give them in tables. Let's look at an example problem. So in this one, we're going to have some mythical gold nugget that gets lost in a snowbank. And we need to find out what temperature it's going to be at. So it's going to have a mass of 365 grams. And it's going to have an initial temperature of 398 Kelvin. It's going to lose 4.85 kilojoules of energy or heat to that snowbank. And its specific heat capacity for gold is 0.128 joules per gram degree Celsius. So the equation we're going to use here is that heat is equal to the mass times the specific heat times the change in temperature. And change in temperature is always going to be the final temperature minus the initial temperature. So taking a look at this, we can look at some of the information that we have. It helps me to pull it out of the problem. So we have a mass that is 376 grams. We have an initial temperature that is 398 Kelvin. We have a heat that is 4.85 kilojoules, and we have a specific heat capacity that is 0.128 joules per gram degree Celsius. So just pulling the numbers out helps me a lot. But with these thermochemistry problems, there's a lot of context within the actual wording of the problem because the sign of something, whether it's positive or negative, is dependent on the context of what is the system and what is the surroundings. Because we're talking about things transferring. Heat isn't just one thing, it's a measure of energy, but it's a measure of energy that's moving from a system to the surroundings or the surroundings to the system. So what's our system and what is our surroundings? And should this heat value be positive or negative? Well, that information is in the problem. It says that 4.85 kilojoules of energy or heat is lost. And so it's going to be lost relative to the system. So that means that our gold nugget here, we're given the final temperature and the heat that's lost from the gold nugget. That becomes our system. And that's because all of the information we have is relative to the gold nugget and not the snow. We don't have the specific heat capacity of frozen water. Instead, we have the specific heat capacity of gold. So gold becomes our system and that snowbank is our surroundings. And because the gold nugget loses the energy, it's going to be a negative value for our heat, and that's key. So the losing of the energy corresponds to that negative value in front of our Q. And that becomes important when we plug in our values to our equation. So to plug in, I'm going to first put in my heat. That's a negative 4.85 kilojoules. My mass is 376 grams. My specific heat capacity is 0.128 joules per gram degrees Celsius. And my temperature change is going to be some final temperature that I need to know minus that 398 Kelvin. Okay. Before I plug this into my calculator, I am noticing a few problems. One, I have units of kilojoules and units of joules. So those won't cancel out. They're not within the same magnitude of each other. So I need to change that. I also have degrees Celsius and Kelvin for my temperature in my specific heat versus the temperature reported. Now, I'm looking at a change in temperature. So I would argue that you can keep this in units of Kelvin if you like. But just to be consistent for our first example, I'm going to change this into degrees Celsius. So to do that, our 398 Kelvin, I'll subtract 273, and that'll give me our temperature in degrees Celsius, 125 degrees Celsius. And my heat, I'm going to convert into joules. And this is a simple metric conversion. A kilojoule is 1,000th of 1 joule. So I can do 1,000 joules divided by 1 kilojoule. So these cancel out, and I'm left with negative 4,850 joules. Okay, I'm going to rewrite my expression now. So I've got negative 4,850 joules is equal to my 376 grams times my 0.128 joules per gram degrees Celsius times my final temperature minus my 125 degrees Celsius. All right, this is looking different, right? So I'm going to rearrange this and isolate temperature on one side. And when I do that, I'm going to divide both sides by this 376 grams. And I'm going to divide by this 0.128 joules per gram degrees Celsius. And I'll do the same on the other side. I'm also going to add 125 to both sides to isolate the final temperature. And so that final temperature is going to be equal to that 4,850, which is negative joules, divided by 376 grams, 0.128 joules per gram degrees Celsius. And I'm going to add to that 125 degrees Celsius. Plugging this into my calculator, I'm going to pause to do that. And so we get a final temperature when we plug this all in of 25 degrees Celsius. So this gold nugget cools to 25 degrees Celsius after it loses 4.85 kilojoules of energy.